All right, welcome back, folks. Hopefully, you had a chance to watch. Looked like all of you had a chance to watch the video, but hopefully, you are all able to get the material presented to you. Again, make sure you take advantage of the time I've set aside to meet with you on during the office hours. So come by and see me if you have any questions about that. Okay. And also another quick note I've posted for you, and I apologize for the delay in getting it to you, but I did post a second set of practice problems for you. So that particular set of practice problems will give you a chance to do practice what we did with the position time graphs and how we can interpret position time graphs, obtain velocity information from position time graphs. So I've set for the first for the homework assignment from that then for tonight. The first 10 questions for that one. That packet has 20 questions on it. So practice use that to practice interpreting graphs, folks. The ability to interpret graphs is a very important skill. So that skill you need to learn. Graphing is such an important part of science, data analysis, whether you're in actually just a general data analysis, whether you're in science, whether you're in business, or whether you're in whatever field you're in, history, regardless, the ability to interpret data, interpret numbers, and make sense of it is absolutely important. And the best way that we can interpret numbers and to find patterns in the numbers is to graph them. Okay, so please make sure then you practice these skills here. And so I think under the circumstances, the silver lining here is that we get to spend a whole lot of time taking a look at graphs and learning, developing that skill to interpret graphs. Okay, and so obviously we're interpreting very simple ones, and we're interpreting only one type of graph. There are many other types of graphs out there that you can that you'll eventually come across, and you have to learn to interpret. But these graphs here, you'll see quite a bit in science and in economics and other numbers-driven fields. Okay. All right. So with that said, please make sure you get the homework done. And if you have any questions about the homework, come on by and see me. Okay. All right. So we left off with the problem here that asked you to basically find the velocity of I'm sorry, the acceleration of this particular car here, this toy car, as represented in this graph here. Okay, so in this particular graph here, let's quickly review what we have here. In this particular graph here, what we were given then is we were given 1, 2, 3, 4, 5 data points. 5 data points for this car with the car, the time in which we start collecting the data at about 10 seconds. So that means then there are other data points, possibly other data points starting at time 0, but here you are presented with the motion of the car from time 10 seconds to time 16 seconds. So we're looking at a 6-second time interval for the motion of this car here. Okay? And the speeds then that were collected are from what here, 0.07 meters per second up to I think here 0.115 meters per second, which I'm gonna have to correct right here. But then we were able to obtain a couple of other data points. We were able to obtain this data point here for the time at 10 seconds, okay, where we start out is by tracing back. Remember that process that we call extrapolation, by extrapolating the line backwards here. So we took the line and we pulled it back. See then where it meets the y-axis there, okay? And we can do the same thing on this side. So the red line here just represents an extrapolation. That means we extend the line from the data point out beyond the set of data points that we have here, and we can obtain more data. This allows us to be able to predict, okay? So these are extrapolated points here. So this is an extrapolation. So we've extrapolated. Sorry. Okay, so we've extrapolated here and there. So extrapolation just means an extend the line beyond what with the set of data points here. Okay. And so the question I think no one's asked yet, and no one's come to see me about, is how do we get this line, what we call the line of best fit? Okay. Line of best fit is a line that we go on Excel or on Google Sheets. I'm sorry, Google graphing, the Google graphing program. Okay, they call this the trend line. Okay, And so this particular line we obtain then by basically taking all the data points and then drawing a line, a straight line, and it has to be a straight line that comes closest to connecting all the dots without actually connecting. So we're not actually connecting the dots. Essentially what we're doing then is we're trying to find then a line that will allow all these points to come closest to that line without actually having to connect. So basically you can think of it as kind of like an average line, a line that comes closest to all these data points. And why do we do that? Because what we can do then is we can use this to find, let's say, then the use the equation. We can use the equation, the point slope equation. So therefore, then we can use this equation then to make predictions about the values for x as we change the values for y. Okay, and so that's why that's where we get this straight line from. It is a line of best fit, and this is something hopefully when you move on to chemistry and physics, and hopefully in your math classes, you'll learn how to generate these lines of best fit. And so again, they're pretty straightforward. The easiest way to do it, you plug the numbers into Excel, and then get Excel to generate the line for you. What we used to have to do in back in the day when I was in school, when we were learning by candlelight, okay, we actually had to plot these data points, take a ruler and physically try to find a line and take the ruler. We had to adjust it back and forth so that we can get a line that comes closest to all those data points. Okay? So that's how we got the line of best fit. All right, so what we do here is we extrapolate the lines of best fit, and so we will get more data points. Essentially what we do then is by extrapolating, we obtain more data points. And that's what we want to be able to do. We are able to predict what the data points should be based upon the angle, this particular line here. Okay. All right. So with that said, then I want to make one quick correction here, and we saw then at 11 seconds here. I had it at 0.15 yesterday. That is not correct. This is obviously not 0.15. 0.15 would be way up there. What this should read then, and make sure you make this correction really quickly, because I asked you to continue this here. Okay, this is going to be 0.115, roughly about 0.115 meters per second. This point lies between 0.11 and 0.12, so halfway up. This would be 0.115. We call this point then 0.11. Okay. All right. And let's continue our line. Let's continue our line here. And I ask you to continue to draw this at about t is equal to, let's see here, 13 seconds. Okay. The velocity here, and I'm going to write it up here. So V1, V2, V3, V4 is going to be roughly, let's see, 13 seconds. We'll call that 0.10. Okay, so that'll be 0.10 meters per second. Continuing on our analysis here, let's do t is equal to 14 seconds. Okay. The velocity here, and I'll stop right here because I'm running out of room here. So we had 0.10, t is equal to 14. We can include the last one. That we'll call that about 0.085. 5 meters per second. And then finally, let's do the last point here. And I'll just write it here really quickly. T is equal to 15 seconds. And I'll draw the velocity underneath here real quickly. I'm running a little bit out of room. Sorry, folks. Okay, so the velocity here then is going to be about 0.07 meters per second. Okay. All right, so we have now plotted, we have shown then a diagram, the picture diagram here, the motion that is represented on this graph here. Okay, so the object here, the car here, is moving in the positive x direction so far. We have a positive x direction because all of the velocities are positive. How do we know that all the velocities are positive? Because they're on the positive side of the y-axis. You can imagine the negative side of the y-axis will fall below the x-axis. At that point, the object then is going to have a negative velocity, but as far as we're concerned now, all from 10 seconds to 15 seconds, all of the velocities are positive, and that's what we have listed here. Okay. All right. And so what I asked you to, the problem I asked you to do that is they wanted you to find the acceleration. Okay. So they want you to find the acceleration. This is constant acceleration. Now, obviously, since these numbers here, these velocities here were estimated from the graph here, these accelerations will not be quite the same, but let's go ahead then and let's calculate for two accelerations and just compare them. We'll call this acceleration, this is acceleration 1, we'll call this acceleration here acceleration 2, this acceleration 3, We'll call this interval here acceleration 4. Okay, so let's go ahead and let's calculate for 2 accelerations and compare them. Let's do the acceleration at interval 3 here. Okay, so the acceleration here is going to be the change in velocity over the change in time, which is the time interval here, which is going to be v final minus v initial, all over the time interval here. Time interval here we'll just call t. Okay, so let's go ahead and indicate what we have. V final here, this time interval is going to be 0.10 meters per second. Okay, minus v final, and v initial then is going to be 0.1. We had here 0.11 meters per second over a time interval from so we're doing A3 here, from 12 to 13 seconds, which is a 1 second time interval. Okay, so if we take a look at this here, then, or we do the math there, it's gonna be negative. Okay, and so we should end up with a negative 0.01, okay, 0.01 meters per second squared. Okay, so that is the acceleration. And for, let me just check this really quickly because I'm getting old and things start. Okay, 0.01 meters per second, so we'll round it out per second squared there. Okay, all right, so that's going to be the acceleration for this time interval here, and I'll just write that in real quickly, 0.01, and it'll be negative meters per second squared. Let's go ahead and find the interval here for the acceleration for this the time interval between 13 and 14 seconds. Again, it's going to be delta v over delta t, which is v final minus v initial, all over the time interval again of 1 second. Okay, so let's go ahead and trace this out here. Then we have then v final for this acceleration here is going to be at 14 seconds, which is we have written here 0.085 meters per second, minus v initial for here for this time interval, which is going to be 0.10 meters per second. And that's all over 1 second. So let's go ahead and plug that into our calculator really quickly. 0.085, which is about 0.9. Hopefully you'll see that it's going to be the exact same answer. Okay, so we have then here rounded to the nearest 100th. Okay, it's going to be 0.02. It's about 0.015. We'll call that 0.02 meters per second squared. So the accelerations are almost the same. We're off by 100th of a meter per second squared, so that's almost identical. Okay, so with that said, then we see then that the acceleration is constant. So we'll call this negative 0.02 meters per second squared. Okay, so obviously the difference here is based upon how we estimated these data points here. Okay, so the acceleration is constant. So we have then acceleration is going to be constant. Okay, and non-zero, which means then the change in velocity is not going to be equal to 0. Okay, which means then the speed, the velocity constantly changes. The velocity constantly changes. So constant acceleration means then the acceleration doesn't change, the velocity changes. Okay, so constant acceleration just means then constant non-zero acceleration just means then that the acceleration stays constant. You have the same acceleration throughout the whole time interval, but the velocity is constantly changing. Okay, so make sure you keep that in mind, so that at constant acceleration, the acceleration stays constant, but the velocity constantly changes. So that's a bit of confusion there, but make sure you keep that in mind. Okay. All right. So with that said, then to summarize what we have here, then we know that the object is slowing down. We have an object that's slowing down for two reasons. Reason number one, we have a negative slope. Okay. Okay. And we see that from the graph here. But if we didn't have the graph, then that we will see that the acceleration is negative and the velocity is positive. These are opposite signs. We have opposite signs for each one of those. And remember, when the signs are opposite, we always have an object that's slowing down. Okay. All right. Very good, folks. So make sure you take a look at this and be able to get this information. So all this information we were able to obtain. So the calculations, the drawing here, and also the summary here. So when we summarized the summary here, when we summarize the motion, all that information is taken from the graph itself. Okay, and so make sure you're able to do that and be able to practice that on the next. So I'm in the process of finishing up putting together the packet for this particular section of our lecture here, and then you'll get a chance to practice this as well. Okay, all right. Let's go ahead then and let's continue on. And so acceleration then, just like with velocity, well, acceleration then we were able to obtain from the velocity time graph. It's the slope of the velocity time graph. We saw then that we can talk about instantaneous velocity. Remember, we talked about instantaneous velocity as being the velocity of an object at a single moment in time. But just like with the velocity, folks, with acceleration, objects do not maintain constant acceleration. Even though we've been doing constant acceleration, over a very short interval of time, it could maintain constant acceleration. But with forces acting on an object in real life, accelerations do also change. And so we can talk about an instantaneous acceleration, which just like what we said with the instantaneous velocity, an instantaneous acceleration is acceleration at a single moment in time. And we can go ahead and calculate for that using limits again. So if we set up our equation here, okay, so we have our equation here with limit with the change here in velocity or the change in time. Remember, with for those of you who've taken physics, this is the acceleration. Then it's going to be the second derivative of the displacement. Okay, so this would be a second derivative for displacement over time. We set that with a limit, but since we're not dealing with calculus here, we can just go ahead and use our equation here of change of velocity or change in time, with the limit now set as the time approaches zero, which means then what we're looking at is we're looking at increasingly smaller and smaller time intervals. So this is the time interval here, folks. Okay, so as the time interval approaches zero, which means then we're getting smaller and smaller intervals of time without actually getting to zero, because obviously if this gets to zero down here, this is an undefined ratio, and so that won't work for us. Okay? And so that's how you could calculate for it. But like just like what we did with instantaneous velocity, we don't have to calculate for that. We can take a position time, we can take a velocity time graph here. Okay, so we can take a velocity time graph, pick a point on that velocity time graph. Okay, so pick a single point on that velocity time graph. And then what we do then is we draw a line that is a tangent. Okay, a line that is tangent to that velocity time graph, which we've done right there. Get the slope for that line. Okay, so once we have that, once you have a line tangent to that particular point there, we can find the slope for that line, and that slope there will give us the instantaneous velocity. So we'll call this the instant velocity at that particular moment in time. Okay, so again, that's taken from the velocity time graph. Remember, from a position time graph, we could do the same thing. We can find then the instantaneous velocity by finding the line that is tangent. Okay, so we want to find a line that is tangent to a point. Okay, and at that point, then we have then our instantaneous acceleration. Okay, all right, very good, folks. So make sure you consider that. I won't ask you to do this, but that's something that you'll see as we as you move forward in physics. Okay? Okay. All right. So with that said, let's go ahead and let's do an example of a problem here where they're not gonna we're dealing with an object in motion. I want you to take about a minute or so to work out this problem here, and then we'll work it out together. Okay, so we have an object here. They want you to find then the acceleration during this interval of time. So here we're not finding the instantaneous acceleration. We're finding the average acceleration. So let's go ahead and get this done here, and then we'll work it out together. Okay, so take about a minute or so to work this out, and then we'll come back and we'll work this out together. Okay, so go ahead and get that done. Okay. Let's go ahead and let's take a look at what we have here. So I would like to just go ahead and draw the picture here first for you really quickly, just as a way that we can kind of situate ourselves and see what's going on here. Okay, so first of all, let's identify what we're given here. Okay, so we were told then that we have a particle here that has a velocity of 60 meters per second in the positive direction. So if this is the velocity at t is equal to 0 seconds, hopefully you recognize that this is our initial velocity here of initial velocity. So we have identified then the initial velocity here. Okay. All right. And so what is the, if that's the initial velocity, what else do we have here? Let's take a look at what else we have here. Okay. So the time interval here obviously is from 0 to 15 seconds. So we can write down then that the time interval, so we're just indicating what we know. The time interval then is going to be a 15-second time interval. And so with that said then, what else do we know here? What else are we given? We are given that the velocity decreases uniformly to 0, meaning then 0 is the final velocity. Okay, so if we write this down, we see then that the final velocity is going to be 0 meters per second. So hopefully you're able to identify all of those on this problem here. Okay, and so with that said then, in order to calculate for the acceleration, let's go ahead and map out what we have here. The acceleration then is going to be then the change in velocity over the time interval. Okay, change in velocity then I'm sorry, let me go ahead quickly. And so we've done these problems. I'm going to quickly finish up here. Change in velocity then is v final minus v initial all over the time interval. Okay, v final here is going to be 0 meters per second. V initial then is 60 meters per second, all over time interval of 15 seconds. Okay, and so therefore the acceleration when we were given this here is going to be negative 4.00 meters per second squared. Okay, so that is the calculated value for the acceleration. Okay, and so you can imagine here, and let's just draw this out really quickly. We have our object. Here's our particle of mass m. Okay, it starts to move in the positive x direction here. Okay, the velocities are positive here, so I want to emphasize that to you. Okay, so at time is equal to 0 seconds, where we start out here, the velocity of this object here is already 60 meters per second. It moves to a time interval at 15 seconds later. Okay, and we were told that at this velocity here, which is represents the velocity final, I'm sorry, this is velocity initial, velocity final here of 0 meters per second. Okay, and so over this time interval here, the acceleration then is a negative 4.00 meters per second squared. And so that's what we calculated for, and this is a picture that allows us to see that. Okay, and so what we did first is we went ahead, and so let's recap what we did here really quickly just to finish out here, folks. And if you please just give me a few more moments here. We identified everything that we knew first. Okay, so we identified what was given. Okay, so we identified what was given in the problem itself, and you had to kind of understand that this was the final velocity. Okay, and then we went ahead and we chose the correct formula in order to calculate for what they ask you for. So this is what's given, and then we make sure we identify what was asked for. So they want us to find the acceleration. Okay, and so if you take a look at this then with the formula that we're given for acceleration, if we leave it that way, is we have then the equation that we need to solve for acceleration without having to rearrange anything. We went ahead then and we substituted in some values here. Delta V represents the change in velocity over time. And then we went ahead and we substituted in our values here. Okay, so we substituted in right here, substituted in our values. Okay, and then we solve for our acceleration. Okay, so that's kind of the process by which you will go ahead and you will solve problems from here on out. And that's what we've been doing up to this point. So make sure you continue to solve problems in this way here. Folks, with word problems, you have to have some systematic way in order to solve for the problems. You can't just haphazardly go about solving problems because that makes it very difficult. So I'll continue to stress this point to you as we continue forward, as we continue to do more problem solving. This is a skill then, folks, that you'll need not only for our class here, but for physics, for chemistry, for any math class. You have to have a methodical way that you go about solving word problems. Okay? All right, so with that said then, what's the significance of the sign of your answer here? Which means then if we have a negative acceleration, what's the significance of this? Well, if we have a positive velocity, which is what we have here, the signs are opposite, which means then that the object is slowing down. So here we're able to do that without the use of a graph because the signs are opposite here. Okay. All right, so very good, folks. So work on the homework for tonight. take a look at this problem here. We'll continue to work out more of these problems as we move forward. But if you have any questions about how we solve for these problems, what we did here, please make sure you stop by this afternoon and get that extra help. Okay. All right, folks. So if not, I will see you tomorrow. Okay. Have a good day.